From Shantenu, yeah.
Thanks, Peter. Thanks you really for organizing everything. Pleasure to be here. Peter's remarked several times on how impeccably timed everything's been. Let's see if for a 15-minute slide with 24 talks, he comments on that after this talk as well. But Augusta's done a great job. He's made my life a bit easier. So of those 24 slides, I can probably literally fly through a few. He's also done a good job by helping lower the effort that I have to put in talking about better, so I can focus on the past. This is about a well-defined science problem done in conjunction with Peter, Dave, who was here, and Christoph, who's on the back, along with members on my back. And although the context is very much about computing areas faster as well as better, there is an underlying hidden story, if not entirely an agenda, about how do we build the software infrastructure to make that happen. Most of you heard me in the morning, but those of you who come in the afternoon, I'm at Brookhaven National Lab and Rutgers University, just outside of New York. Okay, so that's not going to work. So let's set the context. I think everybody is familiar with the fact that we have to get to long time scales, often in a biomolecular simulation. Interesting stuff happens suddenly, but after a very, very long time. And trying to get to this time scale is just one of the many challenges that have been alluded to earlier today. The technology trends that we find ourselves facing or riding are not helping us. We've rode the Mohs and the Dennard scaling for a long time, but one's come to an end, one's almost come to an end. And what this means is that weak scaling will still continue to be easy. We can study some large problems, and we saw some of that in the talk video today. But the strong scaling, so taking a problem of whatever size and running that much more efficiently, quicker, is going to be more and more of a challenge. Just to kind of close the loop, frequencies of chips have not increased. As a matter of fact, are actually decreasing prohibitively. There are a couple of different ways to respond to this. If you have a few extra tens of billions or $1 billion, and you were really sure, you could construct a special purpose computer to try to address this problem of long time scales. For those of us who don't have a few $1 billion lying around, we have to think creatively. One aspect of that creative thinking has been the approach to ensemble simulations, which again, Augusta and others have talked about. I argue in front of you today that ensemble simulations are necessary but not sufficient. By which I mean that running ensemble simulations in a batch mode in terms of a bag of tasks without thinking about how to run them adaptively, by which I mean using the intermediate data to aggregate the state of the simulation, which in turn has to be used to intelligently place in phase space the next set of simulations. Is going to be very important, and without these adaptive algorithms, ensemble approaches in of themselves will arguably not be. So, as a computer scientist, why am I interested in adaptive simulations? Well, they're algorithmically very exciting, but there's significantly more underlying challenges. There's many, many aspects, everything from programming models, which we'll hear about earlier, to more interestingly, and of my own alleys, execution models, which I will allude to. But the fact that adaptive execution of these large-scale workflows is non-trivial, and once again, it's important to remind ourselves of the underlying technology, the supercomputers on which we're running. These have been historically designed to run single large monolithic applications and workflows. Not that they can't, but there are fundamental challenges at multiple levels. So just to get this context correct, I'm going to define an adaptive workflow as one which has the data, intermediate data analyzed, which in turn determines the next set of simulations to be run. But I'm going to focus not so much at the semantics of what's happening, but thinking of the task graph execution, or rather the execution of the task graph. What happens once the semantics of whatever's running is completely lost? And therefore, the abstraction for this talk is that of a task graph. And what really is important to remember is that the task graph is not a simple bag of tasks, but there is a lot of interaction between the tasks across stages, so on and so forth. So different levels of coupling you could use. And there are different types of adaptivity. Remember, the key is not interaction, but the fact that there is adaptive determination of the task graph. This is the execution model we've published recently, which is almost trivial to the extent of being ludicrous, but it's powerful. Our results show that this very simple execution model of take a task graph traversal, execute it, but then have an adaptive signal which captures the adaptivity, but you come back and you are able to modify the task graph and thereby do a task graph traversal, holds for a large range of applications, many of which, but not confined to, are the biomolecular applications. So everything from replica exchange, which we heard some mentions to some more variants of those, and some of which are actually still in active states of development. So to end this initial motivation, I present to you the case that in order to overcome the technology barriers we are facing, not only ensemble-based but adaptive ensemble execution is necessary. In some cases, 3 orders of magnitude improvement in simulation, but adaptive ensemble executions at scale. Remember, this is an exascale project. This is not a single cloud instance or a desktop. This is exascale. We're talking about somewhere between 10 to the power 6 to 10 to the power 9 concurrent NPI simulations. Okay? So this is going to be a non-trivial exercise and requires sophistication in the resource utilization, in the resource management. And whereas if you were just running 10 to the power 9 NPI jobs, that would be sophisticated enough. Add to that the additional complication of the fact that you now have dynamic resource utilization, i.e. all 10 to the power 9 are not available and ready to run at a given instant of time. Some start, some stop, some restart, some crash, some need to be modified. Right? So how are you going to manage the resources at order 10 to the power 9 NPI simulations? And that's what I was trying to say. They require sophisticated software infrastructure, which is why this is an active research topic within my group. Okay. Sorry, and the last part is really this tells us that we should be humble enough and say there's nothing that's shrink wrapped and ready to use. We need to think of the challenges at the different levels, and representing those challenges at the different levels are the building blocks approach to this problem. Again, building blocks, there's the conceptual approach, which I'll talk about. So again, as I said, a lot of my work has been done by Agastya. I'm going to try to show you the power and the challenges of implementing adaptive workflows in the context of biomolecular simulations, and in particular towards computing binding affinities. And Peter alluded to this as well. This is a very important problem for a whole host of reasons, but I reduce it to the fact that binding affinities is a physical parameter of interest that we're interested in computing, and that too using the ensemble-based approach. Again, I guess I talked to you about the TICE protocol. This is just another artistic rendition of that. I won't get into the details of the comparison. The important point which really needs to be reiterated is there are parameterizations between 0 and 1. In the static formulation, we say for a given value of lambda, there are n, in this case 5 replicas, and the values of the lambdas are predetermined. The question of adaptivity, and this is again work primarily on Christoph and Dave, the issue in adaptivity is, can we, as the simulations progress, not only run the 5 at the predetermined value, but based upon progress, can we, using sophisticated algorithms, possibly either rebalance the values or, in this particular case, introduce intermediate values so as to get to our results more effective, efficiently. Right? And so there are two ways to start thinking about the adaptive approach. One is the adaptive quadrature, which I kind of glossed over here. The point I want to get to here is not whether this is good or better, but to remember, you are working with a finite amount of resource. Experiments, think of these simulations as experiments operating under constrained resources. You only have 10 million core hours. You have to be efficient. So if you start thinking of this as an optimal design of experiments problem, you have to say, I'm not just interested in getting the lowest error. If the lowest, calculating that lowest error takes me 100 times more, I'm willing to sacrifice some amount of, let's say, accuracy if I can get there computationally more efficient. And that is why there are different, if you will, algorithms that can develop within Peter's team, which are different approaches to the same problem, but arguably with different, if you will, errors, but also different computational costs. So first level of decision making is which of these algorithms do you choose for a given problem, given a finite amount of computational resources. Again, if you had infinite resources, this would be a meaningless question. And therefore, turning that around, you ask the question, for a given amount of computational resources, can I, assuming I've chosen one over the other, one algorithm over the other, in this case, ties over SMAX, can I run the ties protocol, the ties algorithm, more efficiently? And again, this is assuming the published values as the gold standard reference. What we find that when you run in the non-adaptive mode, for a given amount of computational resources, as defined by the number of thousands of CPU hours, this is the answer you get. And for 4 out of 5 drug instances, you find that the adaptive workflow, remember, in certain values of lambda, is invariably better. A more simpler way of looking at that is for the non-adaptive, as given by here, the errors for a given amount of computational cost are invariably higher than the adaptive approach. And I'm going to fuzz this, but to a first approximation, take this as you fix the amount of compute hours that you assign to a problem, then what are the, so you fix the amount of errors, as in when you let the non-adaptive get to a certain error criteria first, then what is the inverse problem here? What is the amount of computational cost to get to that error value? And you can see once again, for a given value of the errors, the adaptive in green is better than the non-adaptive in most cases. And again, this is an illustration of the details of one particular drug. Okay, so that's starting to tell you that the blind fire and forget approach to workflows at this scale are simply not efficient utilization. And just to kind of calibrate this, the reason why you want to do this is 5. You've got tens, hundreds of thousands of these, so every few thousand hours you save on one means you can do many more. Right? There are different adaptive algorithms we've implemented, again, thanks to Dave and Christoph, and this is another way of saying adaptive termination when you reach a certain error level, so on and so forth. So let's start talking about performance. Exascale is about performance. Exascale is not just scaling a small problem upwards without due consideration. I argue that when people talk about workflows, they do not talk about the underlying performance. And this is just one example of trying to show you that at least up to the scale of approximately 20,000 cores, whatever weak scaling or strong scaling approach to behavior you want, with a set of tools that we've developed in conjunction with the UCL team, you get linear scaling behavior. Now, this is very important. Again, I started off by talking about the importance of strong and weak scaling. This is a representation that you're able to get both in terms of the number of cores, but importantly in terms of the number of ensemble members. So maybe worth unpacking what 2, 4, and 8 means. These are the number of protocol instances. So you're running 8 ties instances concurrently. And within each ties instance, as you heard from Augustus' talk, there could be up to 65 ensemble members. So those would be proficient in maths, 8 into 65, 510. So you're running 510 ensemble members' MPI simulations concurrently and often stopping, starting, rechecking, so on and so forth.
5 minutes.
Okay, thank you. And it's a combination of the fact that a very nice real-world problem with potential downstream impact, but also the fact that this was really done at scale, unprecedented for workflows at least. It's very easy. We saw earlier today 256,000 cores for a single MPI job. Wonderful. Not the same level of ease and sophistication with many smaller number of MPI jobs. No surprises, the IEEE thought that this was worthy of a challenge award. So the question is, how did we do this? Well, not easily, that's the first answer. But this requires a fair amount of translational research between what I alluded to in this morning as conceptual thinking over the past decade. How do you do resource management for many MPI-style jobs concurrently on historically on supercomputers historically designed to run one MPI job at a time? I won't get into the details, but this is HTBAC, co-designed with UCL and the Rutgers Brookhaven team. Lots of details here, but the point I want to get across to you is that this is, and Christoph did correct me, 300 lines of code, 400 lines of code at the top, 1,000 lines of code at the top, HTBAC there.
Yeah,
Approximately 1,000, let's say. So with 1,000 lines of code at the top, you are going to be running these simulations. Now, my point here is that you cannot write 1,000 lines of code and get to scale of the type I've shown you. And this is 1,000 lines of simple Python, not sophisticated C++ or library or system level calls. This is user level Pythonic code. How on earth do you get to these scales and these sophisticated workflows with 1,000 lines of Pythonic code? Well, this is where the power of abstractions come in, and the power of well-designed abstractions that in turn give you underlying functionality. I don't have time for everything, but let me take a 1-minute detour and tell you why I rant against monolithic workflow systems such as everything from Pegasus, Kepler, Taverna to Swift, so on and so forth. They were designed and defined for an era when the design point, the performance point of computational science was very, very different. They were designed in the era when the LHCs of the world were being conceived of, where the ratio of the number of domain scientists and computer scientists supporting them was very different to what is happening in this kind of science we're talking about here. Once upon a time, you had, for the LHC, you had a team of about 50 computer scientists sitting at CERN supporting those workflows. Importantly, there were 1 or 2 workflows in LIGO. I've done the analysis. There are 48 workflows, but 97% of all computational cost is taken up by 1 workflow. When 1 workflow comprises 97% of the entire project, then you can go in and you can optimize that 1 workflow, or you can, and then that's used by several hundreds, if not thousands. That is not the nature of the workflows we're talking about. To a first approximation, 1 workflow, fairly different per domain scientist, often many different workflows per domain scientist. So business as usual is not an option. Also, we're trying to see that now we're trying to get different programming approaches, different tools. And so this vendor lock-in, which again, unfortunately, I don't have time to talk about, is something to be very careful and cautious. But arguably, the most important fact is that the separation between the domain scientist and the developer is no longer as rigid as it used to be. In the LIGOs, in the LHCs from CERN, the separation may still be maintained. But in the science we're talking about here, the domain scientist is often also the tool developer. I think a Christoph or a Dave is a nice example of that. Their algorithmic innovation is embedded in the tools, and maybe the other way around. The tools embed their algorithmic innovation, and therefore this separation of work flows from algorithmic and science is no longer an option. And that is why over the past 10 years we've been working on everything what Christoph was talking about, Saga, once upon a time down here. Slowly but steadily we've been moving up the ladder. And again, this is a talk unto itself, but every conceivable workflow system as being quote-unquote integrated with radical cyber tools, which the point of which is the following. There is no dependency between the cyber tools. If any one of you want to spend the next 10 years of your life designing a pilot system that is better than Radical Pilot, that would be wonderful, because any of the layers above can then use your pilot system as opposed to pilot system that my team developed. Similarly, you can use ENTK. You can come up with a better approach. And this does not happen accidentally. This requires careful software engineering, and there are well-defined properties of each of these building blocks as to what constitutes a building block. And as I said, that's a talk lecture into itself. Okay, so what are the two building blocks of relevance for this particular project and possibly moving forward? The first is the ensemble toolkit. We've heard ensembles, we've heard statistical averaging, so on and so forth. It is fundamental, and you're trying to run this at scale. So without having to develop a capability that allows you to manage the complexity of resource acquisition and task execution, can you have something that gives you a nice, simple programming model to handle the ensembles and the multi-stages? So that's ensemble toolkit in 30 seconds. And and again, this is the performance, which, by the way, just for the records, this is all to do with earthquake science, nothing to do with biomolecular science. Tries to show you that if you're developing components and you can take them from other communities, power be to you, because that means our software development footprint is smaller, and thereby the long-term cost is far reduced. The resource management capabilities are the pilot layer. I talked about this before, I won't go into gory details, but in literally 30 seconds, you take a large MPI job, 1,000 cores, 10,000, 100,000 cores. You send this pilot job, which is essentially an empty container job, and then once you acquire the resources, you are then able to do application level scheduling within this. Very powerful, very simple concept, but making sure that you can keep those 10,000, 100,000 plus cores busy is a non-trivial job. And this just tells you that we have run into fundamental limits of MPI, not Python, but fundamental limits of MPI at 131 cores. MPI cannot spawn jobs fast enough for us to keep all 131 cores. I mention this only because this problem only gets magnified at exascale, and this is small. So, in summary, sorry for taking long, Peter, but in summary, I hope I've been able to convince you that the importance and diversity of workflows is set to increase, especially for the domain we're talking about here. Business as usual is not possible. We need new abstractions and execution models for the workflows. I argue that a manifestation of these workflows, abstractions and execution models are through the building blocks approach. And once you have those, then it is much, much easier to make the algorithmic and methodological advances of the type that Dave and Christoph. Thank you.